I'm Pete Kirkpatrick. I'm a VP Engineering at Pure Storage, and after the intro and a little higher level message, I want to dive into some of our experience implementing QLC and some of the ways we overcame the problems that we encountered. So luckily, I don't have to cover all the high level details, but it is very exciting that we can share this innovation with you today. You know, we did talk about FlashArray C last fall when the product launched. And at that time, contrary to my normal inclination, I made a few forward-looking statements. And so now we can kind of look back on what we've done and reflect on it. And that's what we'll focus on today. One of the most exciting things for me about our progress is that this summer with the Purity 6.0 release, we introduced FlashArray files into the C platform. And that unification of block and file storage here has really expanded the interest and excitement around this product. And so we're gonna keep pushing that and pushing the feature set along with the physical stuff that I'll mostly focus on today. And we'll see where it goes. So really what we did here was react to customer feedback about introducing all flash into this capacity optimized space. And of course, the barrier was always cost, and the characteristics of flash were super desirable, not just in the performance space, but denser, lower power consumption, cooling costs, and all those factors have a huge impact on customer operations as well as just fundamental cost. And so now, I guess what we did originally was we introduced the product with this performance and capacity characteristic, but based on TLC flash, which we were very fluent with at the time. And we emulated the characteristics of QLC flash to ensure that when we introduce QLC, that we didn't change the envelope that we had presented in the product. And so now with actually implementing QLC internally, we're able to provide the same product that we've been able to test and take feedback on for almost a year now. But as Mike pointed out, we've fundamentally changed the economics, and this is going to be a real game changer for the industry. So I promised some technical detail, but I did want to reinforce some of these because they are higher level values that customers are very interested in, but they all have very technical impact. The feature set we have, the attitude we have about quality and so forth really impact some of the higher level business values. So I wanted to emphasize a few of those here. It's the obligatory statement that capacity needs are exploding, and we'll probably talk about yoctobytes or whatever comes after zettabytes soon. But what I want to emphasize there is as that capacity need continues to grow, the footprint in terms of space, power, and cooling and so forth can't scale at that same pace. It's totally imperative that we bring the data center footprint down as we scale capacity. And in this capacity-oriented space where hybrids have been kind of the norm over the last few years, those problems are very, very clear in our customer conversations. And so we really need to drive those physical attributes down so that the environments can continue to scale. And this is true for small business, for enterprise, and into our cloud customers, where those environments can become very, very large, and those problems just get magnified as the system scales. And the other feedback we got about hybrid systems is that the latency inconsistencies come from combining hard drive tier with probably an SSD tier and a large DRAM cache, leads to very inconsistent performance. And so when the workload is friendly to the cache and it's available to that particular application, things can work fairly well. But as workloads are consolidated onto the same system and they compete for those resources, the performance can become very inconsistent. And if you miss in the cache or in the SSD tier, you're going to suffer the latencies of a very high mechanical level access to the hard drives. So that's not just frustrating for the application owners, but it also represents, generally leads to inefficiencies and wasted capacity. And so these are all things that are magnifying the problems that folks have seen and we're addressing here. And then, of course, we can't emphasize enough how much economics matters. It always matters. The current environment has made that even more clear. And it matters to everyone across the same scale. So again, putting the cost of the system down at the right place to compete with hybrids has been, that'll really change the game. But folks that understand the costs of all the other aspects that I've been emphasizing can really see a benefit where this is no longer a fair comparison anymore. And Flash is set to take over the next tier. And we've also seen, kind of moving away from the physical attributes, we've seen a lot of interest or just evolution, I'd say, in workflows and the business models. So everything today, it's a baseline that everything needs to be API driven to enable full automation. And again, that's what allows these environments to scale well. Some of the workflows that we'll dive into a little bit more on data protection, test and development flows are critical. And we have a variety of replication options that are driven to address those problems. Hybrid cloud mobility is another thing that's become table stakes. It used to be a buzzword, and now it's required.
Hey, Pete.
And yeah.
So this is Ray.
Yeah, go ahead, Ray.
So I'm just trying, back to the slide you had before, you indicated that power and cooling don't scale with capacity for hybrid systems, but as those disk drives become multi-terabyte or tens of terabyte types of things, power and cooling actually does scale with gigabytes. I understand the performance.
Oh, absolutely. I'm claiming that it can't scale that way anymore. It does, as the system gets bigger, the power and cooling does certainly grow. I guess what I'm claiming is that it should not, and that's what we're trying to address by using Flash.
And you're saying with the similar types of capacity with QLC, you're not going to see the problems or the power consumption go up as you increase capacity?
Well, okay, so certainly a Flash-based system will consume more power as it gets larger, as long as it stays busy. But the difference between powering a rack full of hard drives and a small amount of Flash, when we look side by side, is it can be order of magnitude savings. Mm-hmm. And so let's take that savings, take advantage of Flash in that way, and then let's continue to work to keep that power down as we make the Flash systems bigger in the lower power space.
All right, thanks.
I do think that's going to become more important over the next several years. Competing with hard drives on power is very simple. But our real competition is the rest of the industry working with Flash. And so we'll compete with each other to kind of similar to what servers have done, where there's a really extreme focus on power savings. So we've also seen the business models evolve, and Mike emphasized some of the value of our evergreen business model, which very much has an architectural component that is a core principle we work with in the hardware. So modular systems that maintain consistent interfaces are critical to be able to swap out components and upgrade portions of the system while keeping the whole system online. And of course, that's very important. But that's starting to evolve. So we're seeing a lot of uptake in our as-a-service business. And this fundamentally shifts the cost of IT from a CapEx model into an OpEx model. And that's very exciting. And that has technical architectural impact as well. So we account for that in the design of our systems, and we really try to make sure that the systems are operating the most efficiently they can in any one of these environments. And it's, again, technical impact. Supporting these business models is high availability, approaching continuous is critical for storage. Nobody can take downtime in modern systems. And so measuring higher availability through upgrades is critical, and folks should do that internally, and they should share publicly how they do, as we do. And so focus on non-disruptive upgrades is also critical so that you can do an upgrade during business hours. You don't have to plan a large outage window. You don't have to notify everyone, and you don't have to come in on the weekends. And then the last part of that is our passionate and proactive support model where we swarm all over problems, drive understanding with customers of what's happening, and even help them debug problems that aren't related to our system. And that's really driving the popularity of our support model as well. Okay, so now we can finally get into some technical details. And again, looking forward to QLC, there was a lot of technical aspects that we knew we would have to address. And now we can reflect a little bit about how that worked and which ones of those were really critical. So I kind of wanted to start with a level set as we start to drill down. How far down are we going to go today? So you can see that we have a FlashArray C sitting here, and all the orange tabs you see across the box, each one of those is a DirectFlash module. You can see that on the left. And on the DirectFlash module, you can see the various black packages, and that's where the NAND sits. So that is a physical NAND package. And then below, I kind of start to, in a cartoon, outline what we call the geometry or the memory hierarchy of those devices. And so, of course, a package contains multiple die. A die is the silicon, of course, where the NAND lives. And a die is generally subdivided into multiple planes. And a plane is essentially the section of the die that's busy when there's a flash operation happening. If it's a write, a program, a erase, or a read. And so there are multiple planes within each die, and we can take advantage of that parallelism as we can across die or the other units of the hierarchy. Each plane is subdivided into blocks. This is the fundamental nature of flash storage, where a block is the smallest unit that you can erase. So that's required to essentially do an overwrite. And blocks are, they used to be single-digit megabytes. They're growing into tens of megabytes and approaching hundreds of megabytes.
Hey, Pete.
So
yeah, when you talk about plane, are you talking about like 3D NAND, where each of the layers would be a plane, or are you talking about a whole stack of 3D NAND?
It's different than the 3D scaling. So it's a logical concept. It's not really, a physical attribute. But think of a plane as a little die. And at some point, due to capacity pressure to continue scaling, as well as performance, the die was subdivided into, you think of it as two little die. Of course, it's on the same silicon substrate. So we can access both in parallel.
Okay. All right, I got it. Thanks.
The 3D attribute is interesting in the sense of blocks, is because once Flash transitioned to the 3D era, where we do add vertical layers, we should call those layers. Those layers are now the scaling vector for Flash. And so when we want to make a bigger die and improve economics, we add more layers. Layer count growing is why the block count is growing, and why that's a fundamental attribute of NAND scaling. And so we need to be very flexible in order to add, say, new flash to the system that needs to commingle with the other flash with a different block size and different other attributes. And that's one of the things that DirectFlash gives us, and I'll kind of show you some detail about that later.
All right, thanks.
Yep. Okay, now these tens to 100 megabyte size blocks are subdivided into pages. Pages are typically what we would go and write. And a page has been fairly steady at about 16K for a long time. So that's now kind of a bite-sized chunk that we can talk about using. But of course, a page is subdivided further into what we call cells. And this is kind of where we'll focus for a little bit. So we won't go too much deeper into quantum physics and so forth. We'll talk about cells at this level. So a cell is actually made of a single transistor. It's kind of a special transistor designed to store charge in a non-volatile manner. And you can find all sorts of interesting descriptions of that. And I won't cover that detail today. But what is important here is that within this one transistor, we can store multiple bits of information. So in the beginning, with 1 bit of information, that was SLC, single level cell. And then 2 bits, MLC, 3 bits, TLC, and 4 bits now where we're landing today with quad level cell. And I'll show you a little bit about how to think about that cell internally. So this is kind of an interesting way for us to visualize how do you store multiple bits in one cell. And so you should think of each one of these charts, each one of the rows as on the x-axis, think of that as voltage. You know, we have a few volts to play with within the cell, and we can subdivide that voltage range into multiple of these peaks, call it, or these distributions. And the vertical axis it's a probability distribution function, meaning if we looked at thousands and thousands of cells that are programmed into all these various states, this is the result of looking at many, many thousands of cells, and that's why we can see a distribution. Whereas any one cell would have, you know, just one voltage level within each of these states. So what we show here is, you know, back in the MLC era, in order to store 2 bits of information, we need 4 states. And you can see that in between those 4 states, there are 3 valleys. And the valleys are actually the critical part, because that's where, and you can see when they get down into the noise, is where they start to overlap. And the critical thing to read from Flash is to try to read in the bottom of that valley to maximize the chance that you're reading the correct bit, and you can discriminate the peak on the left from the peak on the right. And if the program was intended to put the state in the peak on the right, and then we measure it on the left of our voltage threshold, we've got an error. And that's the fundamental challenge in reading these things. So in the middle row, you can see TLC. And so of course, now you can see the 8 states with the 7 valleys between them, and kind of a scaling factor that shows the reduction of the width of those states. And it's probably a little harder to see here, but the level, vertical level at which the states cross over has actually increased. And so that fundamentally is a loss of signal to noise ratio, and it makes it much more difficult to get an accurate read. And then on the bottom row, you can see the QLC. And so now it's getting fun where we have, 16 states and 15 thresholds that we need to use to discriminate. And so here it says QLC NAND modeled, and I wanted to include this because we did this work about 5 years ago, looking forward to the feasibility of QLC, and this helped us understand kind of what we were getting ourselves into. There's a couple other interesting attributes. One I'll point out is the state on the far left, which is in red in these charts, that's the erased state. So when you erase Flash, it will go all the way down to that state. And then programming is targeted to put the charge to move us into the correct set of states above that. And in the MLC era, you could see that there overlapped the state to the right of it just a bit, which got worse with TLC. And now with QLC, you can actually see some of the distribution there overlapping the second state. So that's just an interesting way to visualize how crowded it's really getting in there. So I wanted to emphasize, probably again, some of the fundamental problems that this crowding really leads to inside the QLC. And I chose 2 to highlight here, and I'll talk about a few more in the following slides. But performance and endurance are just fundamental to building these systems, and they're the fundamental problems with QLC. So this really is the core issue that we're facing here. So on the left, I kind of use latency to highlight performance. And it is kind of the core determinant of performance, because you can't overcome latency. Latency of access is fundamental. And really the only thing you can do from there is manage the access, scheduling, and then you can use many accesses in parallel to build up throughput, which is the other part of performance. But in all of these attributes, latency limits everything. And you can see from the SLC era and on, the latency was increasing, but not too much, and fairly linearly, you know, kind of in a manageable way.
Sorry,
but when we get down to, yes, go ahead.
There is milliseconds or microseconds in the
milli, yes. So this is just one access. If you want to write to the flash, this is typically what it will take you to program the flash.
Oh, okay.
So with QLC, you can see we're into a very high range. And the reason is to program the cells as precisely as required to keep them in those really tight distribution locations, we have to do it very, very slowly and carefully. So generally there's kind of a pulse, there's a series of pulses that we use to program the flash. And those pulses need to be controlled very precisely and actually checked. So a program operation does the right pulse and then actually verifies that it landed in the right place.
Hey,
and if
Pete,
it's not, it can be refined a little bit.
What does the read performance look like? Is it this bad, or is it, you know, like an order of magnitude faster, or?
Generally, so reads are always faster than writes. It's the asymmetric nature of NAND, and it's grown in a similar way across the generations, but it's always lower than these. I used write just to highlight one, and what we found is that writes are the fundamental challenge here, and so we really want to maximize the write rate and the sustained write rate especially.
Okay, thanks.
So you can see that just from the numbers that QLC did not just scale like everything else. It really fell off a cliff. And so that's very important in a couple ways. And probably the fundamental way that's important to us is that it means that QLC won't replace TLC in a lot of applications. And in the previous generation, that was largely true. So MLC was an easy replacement for SLC. It took some work, but we've generally the industry has used TLC to replace MLC. And QLC is a different story. And so we actually expect that TLC and QLC will coexist for quite some time because of the kind of extreme nature of this degradation. And on the endurance side, endurance is a concept within NAND that it can wear out. And so the voltages required to drive the quantum effects that program these cells is very high. And that high energy process literally breaks down the oxides within those transistors. And when they break down and start to have defects, those cells can kind of become leaky and they can't retain data anymore, and they can't always program or read correctly anymore. And so endurance is absolutely critical in flash systems. So SLC was kind of a no-brainer. It wasn't a big deal. It can be used in long-term space missions and things like this without necessarily wearing out if you're just a little bit careful about it. And MLC was high enough that, you know, it was a challenge, but in the early days, folks figured out how to kind of get the endurance under reasonable control. And that became the, you know, de facto standard probably starting 10 years ago. And TLC similarly was difficult, but that also hit a key threshold where if you weren't extremely careful, you would end up wearing out systems relatively quickly. And a system that wears out within, even if it wears out in 3 or 4 years, it's all of a sudden going to look a lot like a system that includes hard drives where everything wears out and needs to be replaced wholesale. And you start to have maybe even a forklift upgrade again. So our challenge is to take the endurance, even with TLC media, and make that not a problem. And we do watch the kind of extreme fringe of our field do replacements because we can see the wear out coming, we know what's safe, and we can go and proactively replace that again within our evergreen program, so that the system stays healthy and we keep customers out of the danger zone. It's very difficult for a lot of other vendors to do that. And so, you know, that really ends up representing a cost and these kind of disruptive service events for customers. With QLC, again, we've crossed a threshold where you can't just do the same thing anymore. And so this is one place we'll focus. And you really, really have to have some dramatic changes in the system in order to be able to overcome the level of endurance here.
Just a question to understand also in this slide. So for SLC, we had a very small amount of spare cells available, more in MLC and TLC over time in traditional hard drives. Are you also allocating much more space than actually showed up and externally with QLC devices, or are you taking a different approach? Because, you know, the difference in endurance could also mean that you need a lot of spare cells.
Absolutely. So I'll try to address it now, and I'll dive in a little bit more on that later, but we call the reservation of space within the drive is over-provisioning. Over-provisioning provides kind of an internal sandbox for data management, and it drives, I guess, what's the brief way to describe it? It gives the system a way to groom data in a way that reduces fragmentation, and that allows it helps endurance. You can work within that little sandbox and not drive a lot of overwrites due to inefficiencies that come from fragmentation. We call that garbage collection. So it's pretty well understood that a larger over-provisioning can really reduce the impacts of garbage collection and how that enhances wear. But it comes with a cost. And we see systems typically between, say, 7 and 25% over provisioning. And that's simply 7 to 25% capacity that the customer needs to buy but can't use. And so we consider that pretty wasteful. And I'll show you how we address that and how that's not a problem in our system. Thanks, Enrico.
All right. Just ask a question as well. So you might not have the answer, and maybe nobody does, but are we maybe being too cautious? Because when Flash first came to market, everyone said, oh, the wear is going to be quite extreme. Yep. And now we're, I don't know, 10 years on or whatever it is. And everyone's going, actually, the wear was nothing like what we thought. You know, at the mean time between failure for SLC, MLC, and even TLC is just, it's completely different to what they thought. So I'm just wondering whether you think we're being too cautious, maybe.
Absolutely. So we are cautious by nature. Obviously, we're just going to avoid problems as much as we can. The key is how to do it efficiently. If we're too cautious, we wouldn't ship this product. And so we've really addressed it fundamentally. I actually agree with you. I talked to all of our engineers. Typically, somebody new to the endurance problem will do a quick back of the envelope calculation, and they'll come with wide eyes and say, this is going to fall over in 2 months if you know, when it gets out in the wild. And generally what happens is people don't operate their systems at 100% throughput, which is really driving that calculation down into the months kind of range. So I tried to use another way to kind of visualize some of the challenges that we're experiencing inside these cells. And so I have the same distribution of states across the top. So you can see our 16 peaks and the 15 valleys there. But our characterization team, which I want to give a huge shout out to Yiji and our Flash characterization team, which is really a fundamental advantage that we have in this effort. They shared this data that shows a comparison between the valleys that you'd see in a TLC system and a QLC. So below what I'm showing on the right, it's a zoom in on 4 individual valleys. You can kind of see the arrows showing which ones. And so that that x-axis again is representing the voltage threshold shift, which is what we set in order to try to read down in the valley. And vertically this time it's a raw bit error rate. And so obviously lower is better. And fundamentally, you want to just target your read threshold to land in the bottom of these valleys. So the red traces are representing TLC, and it's kind of before and after some degradation. In this case, that came from data retention, which is just the passage of time. And what you can see generally is that the valleys are generally wide. They're generally a smooth shape. They're well behaved. And so they're not all that hard to hit with a lot of practice. And you can see the lighter red line shows the after retention case, and it didn't move that much. And so, you know, we can handle this type of data retention because our shift didn't have to move around very much, and we're likely to get the right answer the first time or easily within a couple of tries. But this story is very different with QLC, and so you can see the before retention curve in blue and the after retention curves in green. And now, by contrast, these valleys are much narrower, and they move a lot more depending on the amount of the degradation. And so this is the fundamental challenge in reading from Flash, whereas hitting the right spot in that distribution above is the fundamental challenge with writing. So I probably won't go into all the details about what the different shapes mean. That's probably a little too deep for today, but you can see this is just one example of the challenges we're facing. Read disturb is another effect, that reading the data degrades the data, and reading the data degrades the data around it that wasn't even read. And so that's another challenge that's, to Jason's point earlier, it's been well understood for a long time. I've considered read disturb to be somewhat academic until TLC, where it was there and you should worry about it. And with QLC, it's become catastrophic. And so it's just another way that things have become extremely sensitive to these kind of effects. And the last point I have here is in the programming model. So it always takes multiple passes, we call them, of programming to get these states into this tight distribution. And the nasty thing about QLC is you program it and you can't read the data back. The data is not reliable, even right away, before any of the other degradations. And so it takes multiple passes of refinement to get that correct. And so in the in-between state, you have data that you've written down, but it is not reliable and it's not durable. And so we have to manage that very carefully in the system to keep that data buffered somewhere that's very reliable in the case that we lose power and we can't continue that operation. This is just one example, but there are several other attributes like this that make managing of the writes as critical as managing of the reads in the system.
Why would anybody go to QLC with all these problems with, well, reading and writing is just a disaster on this thing?
It's awful.
I mean, my God.
It's fun if you're twisted like me, but it's really, it's an awful problem.
Yeah, it feels like we've invented something where the risk-reward ratio is really off. Not we as the group here, but I meant like the industry.
As an industry, yeah.
Yeah, it feels
well,
very...
we consider our job to evaluate that risk and reward and to mitigate it, of course. And our experience has showed us that this is all doable, but I'm trying to highlight how if you're not extremely careful and really focus on these things, it's very easy to mess it up as well. So I wanted to take a little bit of a segue back to a technology that we've had in place, but really is the core that allows us to deliver on this QLC innovation. This is called DirectFlash. It's a combination of the media module, the DirectFlash module that I kind of showed a picture of earlier, and the DirectFlash software, and they work, you can't have one without the other. So what we recognized when we first introduced this was the same problems, performance and endurance. At that time, we were focused on very high performance. We wanted extremely low latency and high throughput. And this is the technology that forms the physical core of the FlashArray X. And, you know, along when we were working on this, we recognized that all of these legacy disk technologies had essentially defined the early years of the flash era. And so not just disk interfaces, which had become slow because they don't need to be fast operating against a bunch of disks. They don't need to be parallel when a disk operation can take a very long time and is serialized in something like a SAS link or a SATA transaction. But internally to the drives, they were designed to emulate hard drives. Hard drive has a nice linear address space. It just can take a long time to access it if you're not, well, fundamentally. But Flash doesn't have a nice linear access space, and you can't access every bit symmetrically due to the blocks and the geometry that we talked about. And so folks designed in, at that time, it was a great innovation, and it enabled the transition from hard drives to Flash with the Flash translation layer. That's a layer of address indirection that can present a nice linear address space to the host, and it can manage the fragmented and various geometries of the Flash address space down below. So it's that indirection that can manage between those two spaces. And fundamentally, when things get fragmented down in the Flash, that's when the garbage collection within the drive kicks in. That's the killer, because it consumes a huge amount of resources in the system. It's reading, processing, rewriting data all the time, and not exactly where you want it to be at any particular time. And so it's a huge limiter on the throughput. It's a killer for sustained throughput especially, and it causes a huge variation in the read latency distribution when you are trying to get to a particular piece of data. So we kind of recognized those problems, and that was the core realization driving DirectFlash, where we eliminated the Flash translation layer and the garbage collection completely from the drive. This gives us, I'll try to show you some detail on that, but it gives you maybe a 3x advantage on average on really savvy use of the Flash within these systems, and a much bigger benefit if you're comparing to just kind of using an SSD as if it were actually a hard drive and just using it without thinking much about these aspects. So before DirectFlash, Purity had always been designed to accommodate variable media types, and the system has always had multiple media types. And of course, we optimized especially around this nature of NAND flash. But the core attributes of data reduction, whether that comes from deduplication, compression, and other ways, simply means that we write less to the media than the user writes into the system, especially when there's an environment that has a lot of redundancy in it, like VMs or a database. Our metadata architecture is very carefully designed to give good durable access to the metadata, but also to manage it in a way that's not increasing write amplification or driving extra writes into the medium. And then, of course, we have very good scheduling of all the processes in a real-time way. But with DirectFlash, we introduced essentially a platform and a way to easily integrate new media into the system. And of course, in this case, we're talking about QLC, which seems like a big deal because it's been several years since the transition to TLC, but we do this all the time. So we do multiple generations of each type of NAND. We have multiple size die depending on whether we want to optimize for performance or capacity. We have multiple vendors, and all of these things need to be integrated. And it cannot take years and years to do it because there's a 18-month cycle on the NAND die, and we need to get the best die into the market as efficiently and reliably as possible. And so this is really key for us to be able to keep the business operating and keep the product delivering. So technically what it does is it gives us a host-based media management. There's an API between the software and the hardware that accurately describes the hardware and its characteristics. And so that gives the software complete control over management of all that media. It gives software a global view of system state instead of an SSD that can only act on the media that's within it. And that gives us this very wide, but also very detailed view of where data is placed in the system and how we schedule access to that data, both on the read and write side. And again, the fundamental advantage is without that FTL and garbage collection acting there, we expose all of the resources within the module up to software. And to the earlier point that Enrico asked about, there is no over-provisioning here, zero over-provisioning. And so we're able to provide efficiency here, and we can take all of the media that's in the module, manage all of it. Some, for example, in a NAND flash package, you're going to get one of these, and it's got blocks that are already marked bad right out of the factory. We expose bad blocks to the system. We know where every single block is and what state it's in, and then we can choose to, for example, not use bad blocks. But if a block goes bad, we're able to move it, and we can move it within a drive or within other parts of the system to handle any type of failure or problem that comes up. And again, the results are this high sustained throughput and low latency, and we've extended the endurance. So this is the fundamental way I like to describe the endurance, or how we've addressed endurance. And yeah, I've spoken about this in a few areas, but write amplification is the key problem here. So the ratio of writes that we write to the media to the amount of writes that the user actually intended to put in the system is write amplification. And in the earliest days of SSDs, before some of the tricks about garbage collection were understood, this could easily be 10 to 15x. So I write 1 byte to the array, and the array internally has to write down 10 to 15 bytes to make sure that that data is durable. Maybe there's some RAID so you can survive module failures, and maybe you had to write down some metadata so you know where it is. And all of these writes started to become problematic.
So Pete,
as data is overwritten, things get fragmented, and we have to do, again, a garbage collection process to clean it up. And all of those contribute to write amplification.
So Pete, the purity with SSD line here is because of deduplication and compression. You're just doing less writes to the SSD than data coming in?
That's one of the fundamental aspects, but also the way we manage our metadata along with the user data. It's very easy to do that in a way that causes a lot of activity in the drives. And we, how far should I go into it? We aggressively cache all of the metadata in DRAM. And so it's not really accessed all that often in the back end. But we're also very careful to persist all of the metadata, of course, in case of power loss or any other big event. And managing of that is difficult. We've been doing it for 10 years now, and it's one of our core technologies. And that gave us the original advantage that got us to this point. But the orange line represents once we introduced DirectFlash and eliminated garbage collection from SSDs, I'm calling it roughly 3x. I see it vary from this level up to 10x in some of our systems, because we actually have customers that have an older system that's a flash array including SSDs and a flash array including DirectFlash, and they run side by side on similar workloads. And you can actually see this reduction internally when we monitor the systems. And so together, I'd say if you multiply those, it's easy to say that's 10x. Always a nice round number to use. But again, this is the fundamental advantage. And this is my way of showing that we are indeed crossing a threshold. It's not just, it's worse, but this is never really manifested as a problem. So let's not worry about it so much. I think, Jason, this should emphasize why in the MLC era, people talked about this a lot. But even with that naive use of SSDs, you could probably get away with it, right? And maybe only the very fringe of extremely heavy use on arrays would wear them out, but that was very rare. but because the concept was out there, folks talk about it a lot, and you know, it's become well understood by this point. As TLC came along, that was no longer possible. So the tier 1 vendors that you see delivering TLC have come to understand that data reduction and media management is critical to reliably deliver TLC. For a long time, these went into legacy architectures where that wasn't the case, and vendors would essentially replace a lot of the media, and they were used to replacing things based on the failure rates of hard drives. And so, you know, that could kind of keep things running. The problem is that random failures, being random, are not correlated and don't put too much risk for data loss into the system. But wear out is a correlated failure. And if you get to the wear out limit, you're going to really increase the risk of a data loss event. And again, with hard drives wearing out and having a correlated failure mode, again, at a much higher level, that's why forklift upgrades appeared. And so for a long time, folks were actually applying that same model to their flash as well. So now with QLC, we're getting really into the danger zone where the techniques developed for TLC are not good enough anymore. And you can see the QLC limit down there on the left, and we strongly believe that these kind of techniques are going to be required for anyone to deliver a QLC array that's reliable. So it's easy to put this stuff in an array. If you want to make it reliable, and if you value that as our customers do, it's critical that we don't flirt with that limit anymore. So we need to be well below.
So Pete, we've been talking to other vendors throughout Storage Field Day, and there are other vendors that are using QLC, not, I would say, in a naive perspective, but trying to, you know, do writes, large writes and stuff like that. Sure. Is that adequate to keep a QLC drive in the okay zone, or do they really need to get down to the level of media management, no flash translation layer, no garbage collection, those sorts of things?
So that helps. That certainly helps, and that's one of the techniques that fed into, let's say, the first step is data reduction can help. The not naive use of SSD is just what you described. Trying to do large writes and trying not to do a bunch of small overwrites is fundamental to keeping the fragmentation down. And so managing that data in the operating system at the array level is important. That's one of many techniques that I'd say contributes to our first step with purity. Certainly that's not going to be adequate for QLC. And one way that some of the early QLC vendors have gotten around that, at least to this point, is over provisioning. And so you can get a QLC packaged in an SSD. It's over provisioned to the point where it costs about the same as a TLC drive. And so that's not a trade-off I want to make. I don't want to take on all these challenges and pay the same amount. And so what's underlying everything here is that, yeah, there are other ways to solve these problems. You have to solve these problems in a way that's extremely reliable and efficient, being cost efficient, or you haven't necessarily made progress.
All right, thanks.
Thank you. So this was fun. I really like space, and I really like all the data analysis and data engineering that we do, and so I try to combine those into this picture. But we are obsessed with monitoring our systems in the field. And the nice metric is we have billions of blocks within DirectFlash that are active in the field. And we gather statistics and events from those blocks every 30 seconds. That's a huge amount of data. And we've developed a very sophisticated pipeline that we use for this, as well as every other attribute of our systems. And we can really use it to monitor in exquisite detail what's happening on a single module, on a single array, and all the way up to trends within our fleet. And so we can use this to compare NAND generations to each other. We can compare the quality of our firmware and software. we can look for physical problems, and we can really develop a nice view of all types of NAND. So this helps us keep everything healthy in the fleet, and it also helps us gain insights into what we'll deal with in the future. So this is one of the things that led us to develop QLC, but also this is how we know that it's working well. I wanted to pull out one metric here, and of course, I had to obscure all the axes as I like to do. But I've talked quite a bit about availability and how critical that is to a storage system. And reliability is fundamental to delivering good availability. And it's not just that servicing the failures is kind of a pain and it's expensive, but again, you need to have quality of this level if you want to deliver the solution efficiently. So again, you can compensate for all sorts of quality issues with things that cost money. And if you want to do it correctly, you really want to get the reliability in fundamentally the right place. And then that allows you to deliver an efficient system. So again, these are return rates within our own fleet, between the SSDs in our fleet and our DirectFlash. And you can see that we're consistently multiple times lower failure rates in our DirectFlash modules. This is a big advantage. I guess I should point out, we proposed that this would be true when we were developing DirectFlash at the architectural level. And maybe you could call it hope. You know, it's a reasonable argument, and we hoped it would manifest in real life. And now, after several years of doing this, we're able to validate, and this is probably the first time we publicly share that it's actually quite true. So I thought these images were a great way to kind of pull everything back together, again, focusing on these core issues of endurance and performance. So on the left, we have Eliud Kipchoge, who recently broke the previously thought impossible 2-hour barrier in the marathon. And it's funny because he has high endurance and very high performance, but let's focus on his endurance for this one. And again, you know, the problem with QLC is that if you don't manage that endurance, you will wear out and drive yourself into danger zone territory. And then all the attributes that I described within Purity and DirectFlash are how we address this head on and minimize that risk. And then on the right, you've got the fastest human on earth. That's Usain Bolt from Jamaica. And it's funny to talk about, I've said this many times, I talk about high performance. And then out of the other side of my mouth, I talk about how low performance of the QLC is. So to bridge that gap conceptually, we need to think that when you have a low performance media, especially with this high latency attribute, you have to be extremely careful about how you schedule to it and manage it in order to provide reasonable performance at the product level. If it takes many tries to read from flash, that starts to not just delay that operation, but it starts to congest other operations, and we have conflicts there. That way, latency can really build on itself in a nonlinear fashion. And so similarly to the reliability attribute, if you don't get all of these aspects really perfect, then the system can kind of really fall behind. And I think this is what folks will observe in a lot of other QLC systems if the design is not attended to very carefully. And then some of the other attributes that I mentioned earlier and how we address these, the reading and, you know, trying to hit the valleys that we talked about. To do that read optimization doesn't just take good NAND characterization. And, you know, we're not the only folks in the industry that do good NAND characterization, but for QLC, it takes deeper characterization. There are more pages to characterize, there's more variability. And the variability is really important, and that's why I say wide. You can measure, you know, a handful of blocks or a handful of die and a handful of blocks on each die and build up a data set that can tell you how MLC or TLC will behave over its lifetime and due to read disturb and retention and so forth. With QLC, we've observed a much higher variability from die to die and block to block and page to page. And so fundamentally, to do that well, we have to increase the volume of our characterization. And one thing that I think has become clear internally to our team is that we characterize in the product. So the very first NAND we get from the vendor, we pop it onto one of our DirectFlash modules, and we have a special library that can go and focus on doing the characterization routines. So when we want to scale that up, we just build more drives, we put them in more product, and it characterizes itself. So not only does that help us do kind of the lab work that sets up for perfecting our algorithms, but we have immediate feedback on how that worked when the array is running in our development environment. And then, of course, as I emphasized earlier, once it's out in the field, we're still monitoring it. So you could say that our characterization is an ongoing process, kind of from cradle to grave. And we're continuously validating that what we measured in the lab is manifesting in real life.
So Pete, a lot of this read disturbs, characterization of NAND, read optimization, retention, those sorts of things, typically are done by SSD vendors for a specific NAND technology. I mean, I understand where DirectFlash gets the advantage of being able to get down to the NAND and eliminate a lot of these, the bulk problems with garbage collection and over provisioning and that sort of stuff. But I'm just, a lot of people, a QLC SSD has done what they can to do every one of these things, right?
The problem is they have a limited scope on which to act.
But these are SSD vendors. They've got all the NAND in the world to characterize, right? Sure.
We characterize more NAND than the vendors do.
Really?
And of course, we measure NAND from all the vendors, and we do it very, very thoroughly. And when an SSD vendor ships that SSD, the only time they get it back is if it failed. And often they don't really, they will do failure analysis, but typically, they chalk that up to, we had a, X% failure rate. This cradle to grave monitoring and closed feedback between what they tell us their characterization looks like, what we measure, and then what we experience in the array, nobody else can do that. And then by scope, what I really mean in parallel is that they can only act on mitigating these effects within the scope of a drive, because any one drive is not aware of anything else. And so this is where the global view of the system comes into play and really gives us an advantage. If we see that one die within one drive is weak, right? It hasn't failed, but well, it sure looks weak from the feedback we're getting. We can turn off that die. We can go and place data elsewhere within that drive or in another drive. And that's just one example of how we can manage state better than an SSD can.
Okay, thanks.
Yep, thank you. So one last point on the read optimization is bit error rates with QLC are fundamentally higher. So the bottom of the valleys that we looked at before, you can't go below the bottom of the valley. So that represents sometimes the worst case bit error rate. Soft decode LDPC, which is low density parity check. This is our error correction technology. It's in common use these days since TLC and MLC, TLC and later has become the de facto standard. We found with TLC that it was not important to utilize the soft decode, which is slower but much more careful and powerful read that can lead to more likely success. And so we've turned on soft decode here, something that was available from our controller technology. We just decided this was the point to turn it on. For read disturb, one of the interesting things we did was, if you think about the nature of read disturb, you can design a cache that specifically addresses it. And we were able to do this not just from characterization and the design of the cache, but because there's no FTL in a DirectFlash module, there's basically DRAM sitting around unutilized. And so we decided this was a great way that we can't put a smaller DRAM down because we're using the smallest we can physically place. Even that is largely unutilized. And we decided this was a great way that we could mitigate read disturb, and it's very effective. For retention, you can't avoid the passage of time. And so we go back to fundamentals. You minimize the wear so that you don't have the combination of retention with wear out and the read disturb problem. But also we found an innovative way to offload the data movement. And maybe Ray will point out this time that, well, if an SSD is managing this stuff, it is an offload of the data movement. But since we have a host-based FTL, we have to have an interaction. So the host is still directing where the data is, but the data movement is performed by the drives. And then with multipass programming that I mentioned earlier, you do have to be extremely careful with buffering because power loss is a thing. Repeated power loss can be a thing, combined with bad temperatures. And we see all sorts of bad things happening in the data center. And so this is an area where we paid special attention and to overcome the right problems within QLC. So that's kind of the technical content that I wanted to cover. And so thanks to Mike covering a lot of the higher level points, we won't spend a lot of time here. But it is very, very exciting for us to be able to provide all flash into the capacity optimized space in a way that's fundamentally going to change the economics and change that space. The latency, again, is very predictable. Of course, it's higher than a FlashArray X, but the consistency there is what a lot of folks value. And then the density here is unparalleled. So this example is saying 5.2 petabytes. That's an effective after data reduction. And that's in the 9U footprint you can see there. But the easier soundbite is that we can do 1 petabyte raw capacity in 3U. And I'm not aware of anywhere else you can achieve that. Of course, we changed the next one from optimized for QLC Flash into built out of QLC Flash, and that's satisfying. But again, that ability for us to test the market space with the product before we had the technology ready really paid off for us. And we not only got into the market early, but we got the critical feedback from customers to get this product right. And you know, even with all of these nasty problems that I talked about solving, we do not compromise on our enterprise experience. And so the availability, the simplicity of the management interface, all of the APIs, and all of the vigorous and proactive support that we provide, everything applies here. So this is really part of the FlashArray family and really part of the Pure portfolio with FlashArray C, FlashArray X, and FlashBlade, along with all the cloud offerings. And so everything can really work together efficiently. So again, we did Purity 6.0. I think it was released in June. And these are just some of the new attributes there that I won't go into all the details, but they really highlight some of the key higher level innovations that we combine with the media innovations that I'm talking about. Files, again, is the thing that's, I think, is really a game changer here. NVMe Fabrics is now supported. Specifically in this case, we've got some VMware certification, which is really going to expand the market there. And that's a funny one, again, to talk about performance. You know, you think of NVMe Fabrics as a high performance interface, but we've got several FlashArray C customers that only use NVMe Rocky with these arrays, basically because it's becoming a de facto standard for several organizations, especially in the cloud space. You can see the variety of hooks we've got into the different clouds and between clouds. And of course, we've got the support of Pure One with its expanding feature set, and everybody loves Pure One. So all of this is really coming together in the portfolio. And we'll start, or I guess we'll end right where we started with kind of a view of that portfolio where we really are covering all aspects. It's not just performance and capacity, but it's what type of performance. Are you really prioritizing low latency in something transactional or a high performance VM? Are you prioritizing high throughput, which is really where FlashBlade shines with our scale out architecture? Or are you willing to compromise on performance and optimize around cost? And that's obviously where FlashArray//C is targeted, and we're very excited to provide that to customers. And we're very excited to hear more feedback from yourselves and everyone else.